Hi, students, welcome to video 25 on mining mechanics. So first we need to understand the difference between a rock and a mineral. A mineral has 5 characteristics. It's naturally occurring, inorganic, meaning it was never alive, solid, has a definite chemical composition. Quartz, for example, is SiO2, and a repeating chemical or crystal structure, different pattern. It can be a shape, basically. A rock is a combination of one or more minerals. So in this picture over here, these are both quartz. This is amethyst quartz, and this is just clear quartz crystal. And if you add quartz and a bunch of other minerals together over here, you get the rock granite. So the white pieces are the quartz, the pink is a different mineral called feldspar, and then the black is like a muscovite mica. So some examples of minerals and rocks that we use. For energy, we use coal. That's a sedimentary rock. Uranium is a mineral or a element that comes from the mineral uraninite. Metallic minerals that we look for: aluminum, iron, copper, gold. Non-metallic minerals are actually the most abundant in terms of the mass that we actually mine for. So we need a lot of sand and gravel. We use it in buildings. We use it in roads, making concrete. For fertilizer, we need phosphorus rock. Phosphate rock is where we get phosphorus from. Gypsum we use in drywall, so we need that. Halite is table salt. Those form when water evaporates and the salts are left behind. And then in my other building materials, we use a lot of things like limestone, marble, granite. You might have granite or marble countertops in your home. One thing to remember is these are all non-renewable resources, meaning once they are gone, they are not going to be replaced in human lifetimes. So looking at the crust, we have a bunch of different elements that make up the minerals. The biggest two to remember are silicon and oxygen. Oxygen is the number 1, silicon number 2. So most minerals are going to have silicon and oxygen in them. They're called silicate minerals. And so, for example, SiO2 is quartz that has silicon, 1 atom, and 2 of oxygen. And this is what basically all sand is quartz. When we look at ores, ore is metal or mineral that's extracted from a rock profitably. So most of the time when you just go underground and you pull up material, there's minerals that are attached to the rock. They're not just sitting there. Like there's not usually just gold underground. So it's going to be in an ore form, which has the metal or mineral attached to it. So if it's a high grade ore, it is a large amount of that mineral attached. If it is a low grade, it is a small amount of that mineral. So how are different minerals made? Most of them are made from crystallization of magma. This is how you get igneous rocks. So when igneous rock cools, the little crystals inside it, or the minerals, they can crystallize and form things like gold or silver or lead. We also get hydrothermal vents. That's what this picture down here is of. Hydrothermal vents, just think volcanoes sort of underwater. And you have things like sulfur, copper, lead. These are also associated with normal volcanoes on the surface. We have manganese nodules. These are seafloor deposits that are like in this picture over here. They have a bunch of different things, but manganese is where we get a lot of these. This is very controversial because we argue about whose these are. They're kind of like, who owns the sea, kind of back to the tragedy of the commons idea. Sedimentary processes can also form minerals. So placer deposits, think about like river panning. This is basically you're going down and getting things that are deposited with water. Gold is really common for this. Evaporites, again, water evaporates and leaves behind things like halite, gypsum, borax, which we use in cleaning as well. So how much do we actually have? We have some identified, we have reserves, and then we have the hypothetical undiscovered. So identified minerals are things that we know the location of. We are currently mining them. We know the quantity and the quality of them and where to get them from. So these are kind of like your identified over here. Reserves are ID'd, but we haven't extracted them yet. Maybe it's harder to, it's not as easy to get to those, but we can actually get them. And then we also have what we call undiscovered. So we think these are potential supplies that probably should be there based on how much we found. They're assumed to exist, but we really don't know whether or not they do. So there's a good possibility that maybe they don't, and we're never going to find them if they do, or they're too far down. We don't have the technology for it. So looking at where minerals are located, the main idea here is to understand that they are everywhere. So basically every country, every continent has minerals that can be mined and processed. If you look at the United States, we have a lot of iron. We also have a lot of coal, especially out in the middle areas. We have a lot of oil that we're getting up. Copper you also see, and a little bit of silver in the United States. Right here in North Carolina is iron. There's a bunch of others, but these are just kind of looking at the main ones. How do we use these things? You need to have a couple of examples. Gold is in not just jewelry, but electronics. So your cell phone, computer, everything electronic basically has a certain amount of gold in it. We're talking very small amounts. Aluminum, we know about aluminum cans, but we also use it in cars, airplanes. Steel will also be in vehicles and airplanes. It contains iron. We use it in buildings, anything you want to be very sturdy and not fall. Sand, we use it to make glass, bricks, concrete, and limestone we have to make cement, concrete, and other buildings. Most tombstones, for example, are made out of either limestone or granite. So this is kind of a infographic showing you how much you use on average. So every American born will need. So if we look at a couple of different things that we know about, almost 38,000 pounds of salt in your lifetime. Not only is that salt that you eat, but it's also salt that, for example, we put on roads when there's snow. We also use a ton of phosphate. We use 7.08 million cubic feet of natural gas. 73 almost 1,000 gallons of petroleum, cement, copper, you name it, we use it. And this is not all that we use. And this number was given in 2016, and it kind of continues to go up. So looking at the life cycle of a metal, these are some terms that you should understand that deal with mining. So first you have to go in and remove the overburden, which is the layer of rock overlaying the mineral deposit. You also have gangue, which is basically the worthless material that we don't want that surrounds the ore. It's part of the overburden, but it's not actually overburden, and you're removing that. Smelting is the process that uses heat and chemicals to turn these metals and minerals into actual usable products that we want. The tailings are the piles of waste that are left behind after we have extracted the material. It does contain gangue. They basically just sit in these big piles. And spoils are the unwanted waste after mining on the surface or the subsurface. So tailings are all basically on surface. Spoils also includes subsurface mining. So looking at some surface mining, here's some techniques: mountaintop, open pit, strip, both area strip and contour strip. Placer and dredging. Here's some pictures of these different things. We're going to go through each one of them and talk about them. So in surface mining, you're removing the A, B, and C horizon, and you're trying to get down into that bedrock. 90% of our non-fuel resources are mined with surface mining processes, and 60% of coal is mined surface mining, mainly this strip mining over here that we're going to talk about. It might help to draw a picture for these things. Subsurface mining is when we go down and we remove really deep deposits that we can't just take the overburden off because there's just too much. A lot of times we're looking for coal and metals, and we basically drill vertical shafts, kind of like in this picture over here. We drill down and then we build tunnels. We either blast them out or we drill them horizontally. Different types of subsurface mining are room and pillar. We have longwall, and fracking is also technically a type of subsurface mining. So looking at open pit, again, big, huge hole in the ground. That one's pretty obvious. A lot of times we're looking for iron, copper, gold, gravel. There's a big quarry in Wake County called Wake Stone Quarry near Knightdale. And basically it's just a big hole in the ground that we try to get sand and gravel from. Strip mining is when we basically take strips off the surface, and they're horizontal bed layers. This is really good for coal. Area strip mining is in a flat place. Contour strip mining is if it's on a hill. We're like taking, chunks off of the hill. And a lot of the coal is dug this way. So 70% of coal is mined using strip mining processes. So surface mining methods, another one, mountaintop removal. It's basically exactly what it sounds like. You're taking the top off of a mountain. As you can imagine, this is going to cause lots of environmental problems. We do this a lot in the Appalachian Mountains, and usually we're always looking for coal. Dredging is basically taking a big scoop, imagine, and hitting the surface of the water, underneath water. So you're basically taking a scoop and trying to pull up anything that's underneath the water. Room and pillar, remember this is subsurface, so basically you're creating rooms underneath the ground. They're held up by these pillars, and the ore is hauled to the surface. Usually you're using dynamite underneath the ground to create these tunnels. Longwall, you're creating kind of like a really long tunnel instead of rooms, and you're digging narrow tunnels that are supported by these pillars. So good thing about the longwall is there's not going to be any tunnels left to collapse once the mine is abandoned, because the tunnel basically just collapses in on itself as you're going. So the last thing we're going to talk about are depletion curves. This is also in your book. I think you did it on your concept card. So there's 3 different scenarios. Either A, you can mine something, use it, throw it away, never make any new discoveries. The price is going to shoot up because you're not using, you don't have as many resources. So depletion time is very high here, or short. You don't have very much time to use the materials. It's not a very extended life. That's your first situation. Very unsustainable. Second situation is you can recycle materials. Maybe you increase the reserves because you improve your mining technology. Your prices are still going to be a little bit higher, but maybe you had new discoveries. So again, you're extending the life of the products. You're extending the non-renewable resource. And finally, in C, you have recycling, reusing, reducing consumption. Again, we're finding increased reserves. There's always going to be higher prices, but we've got new discoveries. So the difference here is where we're using and reducing our consumption in C. And what you'll see is the time that you have, the lifetime of these resources will go much, much higher if you are doing these things and not just throwing everything away and you are actually recycling them. So the key to take from this is that we don't want A, we want the sustainability, which would be C. So C would be sustainable resource use. A is very unsustainable resource use, which unfortunately we're falling somewhere along the line of B right now. So there's definitely room for improvement. All right, come ready for a quiz and any questions.